Hello everyone, and thank you for watching Edupedia World videos. In this video, we'll look at the concept of weak electrolytes. We'll go into its definition and how weak electrolytes behave when in solutions. So what weak electrolytes are, we have already seen the definition in a previous video, that electrolytes for which the dissociation or ionization constant is very low. For example, if I have an electrolyte AB, so in aqueous medium, when this AB dissociates into its cation A positive and its anion, that is B negative. So when this happens, the equilibrium constant for this reaction, for this equilibrium, okay, that is K ionization or K dissociation, okay, or the equilibrium constant KEQ, which we know is equal to concentration of A positive into concentration of B negative divided by concentration of AB. So this dissociation constant or ionization constant is going to have a very low value. This means the numerator here is going to be much less than the denominator. Okay, so that is the reaction here, we can say, is shifted in the backward direction. Alright, the concentration of product is very low in comparison to the concentration of the reactant, and hence the equilibrium is shifted in the backward direction. Hence it is a weak electrolyte. This means it is an electrolyte. It does furnish positive and negative ions so that electricity can be conducted, but that furnishing of the ions is very low. Pretty much all of the electrolyte remains undissociated. Okay, it remains in neutral form itself. So how low a value of K equilibrium is considered to be very low? So weak electrolytes are going to be electrolytes for which this equilibrium constant of this dissociation or ionization reaction is less than 10 to the power minus 3. So whenever you are given an electrolyte in the exam for which K ionization is less than 10 to the power minus 3, it can have any value, 10 to the power minus 5, 10 to the power minus 14, okay, any random value which is less than 10 to the power minus 3, you can assume it to be a weak electrolyte, and whatever analysis we will see now is applicable over there. So since here K ionization is very low, the dissociation of the electrolyte in the forward direction is very low. Hence we can say the degree of dissociation or the degree of ionization alpha is also going to be very low. In fact, it is going to be so low that we can say alpha here tends to 0. Alright, that is, the equilibrium is pretty much shifted in the backward direction itself. Alpha tends to 0. So what kind of electrolytes are weak electrolytes? Which all electrolytes come under this definition? Again, there are several examples. All the weak acids, okay, weak acids which you might have heard of or which you are going to look at later on. For example, acetic acid, okay, HCN, H2S, all these are examples of weak electrolytes. Weak bases, okay, weak base like ammonium hydroxide or aqueous ammonia, alright, FeOH whole thrice, zinc hydroxide, aluminium hydroxide, okay, all these are weak electrolytes. Similarly, there are several salts which act as weak electrolytes. Okay, so all these weak acids, bases and salts are examples of weak electrolytes, and the analysis that we are going to look at now will be applicable to all of them. So let's go into the mathematical perspective of how these electrolytes behave when present in water. So say I have a weak electrolyte HA in water, that is in aqueous medium, and upon dissociation we know that it is going to break into its cationic part, which is H positive, and its anionic part, which is A negative. Okay, and let's say the ionization constant for this reaction or the equilibrium constant for this reaction is given to you as Ki, and we know that the value of Ki is definitely going to be less than 10 to the power minus 3. Why? Because it is a weak electrolyte. So say initially at T is equal to 0, you had dissolved HA in concentration C, that is the molarity of HA was C in water, and the amount of H positive and A negative was very insignificant, that is 0. So at equilibrium, what will happen is, I can assume that the degree of ionization here is alpha, so the equilibrium concentrations will look like this, C into 1 minus alpha, this will be C alpha and C alpha. Okay, we have already studied writing equilibrium concentrations in the chapter of chemical equilibrium, so this is not a problem. Okay, now we have also studied how to write the ionization constant Kin. It is simply going to be the product of concentrations of H positive and A negative divided by concentration of Ha raised to their respective stoichiometric coefficients. So K ionization from here is going to be C alpha multiplied with another C alpha divided by C into 1 minus alpha. That is, it is going to be equal to C alpha square by 1 minus alpha. So now to find the degree of dissociation alpha and to find the equilibrium concentrations of each of the constituent substances present over here, you can solve this quadratic, okay, if you know the K ionization value, which will be given to you in the exam, okay, or wherever you are studying from. Alright, and using this quadratic you can solve for alpha. Okay, but a simple way to do this, okay, and which is not a really bad method, it is an approximate method but it still gives pretty good results, is that since it is a weak electrolyte, we know that alpha is so low, it can be assumed that it is tending to 0. It is not 0, but it is tending to 0. Okay, so what we can do with the use of this is, by assuming alpha is tending to 0, we will be able to neglect alpha with respect to 1. Okay, why is that? See, it's pretty simple. It's like if you have 10 rupees with you, okay, if you have 10 rupees and out of those 10 rupees I say, okay, then this is all the money you have, okay, you have never had more money than 10 and this is all you are going to ever get. So if I ask you, like, give me 1 rupee out of this, you are not going to do that, right? If I say give me 1 rupee, it's pretty high value for you. If you have only 10 rupees, then 1 rupee holds quite a significant value for you. But let's say if instead of 10 rupees you have 10 lakh rupees. Okay, so if you have 10 lakh rupees and now if I ask you that come on man, give me 1 rupee, I need it, and you know I just need to make a phone call, let me take 1 rupee from you, you will be like, okay, I will do you this favor, keep this 1 rupee. Okay, so this is not a problem for you, right? So that means the amount which you are neglecting, okay, that is 1 rupee over here, depends on with respect to what it is being neglected. Okay, so 1 when trying to neglect it with respect to 10 is a bit problematic, but when you are neglecting 1 with respect to 10 lakh, yeah, it's not a difficult problem, right? Yeah, go ahead, neglect 1. Okay, even if you add 1 to 10 lakh, it doesn't really matter much, and if you subtract 1, it doesn't matter either. So that is why when alpha is so low that it is tending to 0, I can say that 1 minus alpha tends to 1. That is, I can neglect alpha with respect to 1. Because even if you are going to subtract alpha from 1, it's going to be like, 0.9, 0.95, something like that. So that doesn't really matter. Alright. So in general, in fact, in this chapter and anywhere else, whether it's in your physics subject or chemistry or maths, if you are adding or subtracting two values A and B, okay, and if you want to get the exact magnitude upon calculations, you can take an approximation. You can neglect B with respect to A. Okay, you can neglect B with respect to A and assume that A plus minus B is approximately still equal to A if B is less than 5% of A. Alright, so this 5% of A, that is, let's say if A was 1, then if B is less than 0.05, I will neglect B definitely. Okay, I will not worry about whether I should add it and subtract it. I will simply neglect B and take my A plus minus B as approximately equal to A. So about this 5%, it's not a rule that you can always take it as less than 5%. Okay, in your examinations, especially in JEE examination and your school class 11th and 12th examinations, irrespective of which board you are in, you can even neglect B when it is less than 10% of A. Okay, that is, margin of error that you have with you is higher. But if you are doing a scientific analysis and you are a very good scientist and you want to do a very rigorous and accurate analysis, then you might even neglect B only when it is less than 1% of it. Okay, so it's not like a fixed law or a rule. Okay, it's more of a rule of thumb. So you can take any value to, lower your margin of error or to increase it. So usually in our analysis, we'll take it as B less than 5% of A. Okay, but in your exams, to make your calculations easier, you can always neglect B even if it is less than 10% of A. Okay, so even if your B is like 0.09, okay, and A is 1, then you can neglect that. Instead of writing plus 1 plus minus 0.09, you can simply neglect 0.09 and assume it to be 1. Why? Because 0.09 is less than 10% of A. Alright, so this is what we will do here. So we know that K ionization is equal to C alpha square by 1 minus alpha. So now instead of solving the quadratic, okay, and using the quadratic formula, you will simply neglect alpha. Okay, don't use Siddhacharya formula, just avoid it. Okay, it's going to make your calculations difficult. So instead just write alpha C alpha square is equal to K ionization approximately. Okay, it is not the exact value. So alpha here is approximately equal to K ionization by C. Alright, so this is the value of alpha which we get upon neglecting it with respect to 1. In fact, what you should always do is, once you get the value of alpha from this, okay, so whatever value, whatever magnitude of alpha you get, calculate it and then check whether that alpha was actually less than 10% of 1. Okay, or less than 10% of whatever you had over here. Okay, so if it is less than 10%, then this neglecting part was right and you can move on with your further calculations. But if it turns out that after neglecting the alpha comes out to be at a value higher than 10% of 1, then you can't neglect it. That means you will have to go back. Okay, you will have to assume that these calculations are wrong and then again go back over here and solve the quadratic formula, get the answer of alpha, exact answer of alpha, and then move on with your calculations. Okay, so simple ways to always neglect alpha, whenever it is added or subtracted to something irrespective of what it is, 1, 2, 0.2, always neglect alpha. Then find the value of alpha after neglecting and just verify quickly wherever you neglected alpha, was that right or was that wrong. Later on you will see this will simplify your calculations a lot. So this is what we'll do in weak electrolytes always. We'll neglect alpha and then we'll verify if it was nice enough to neglect or was it not. Okay, so this means alpha here comes out to be equal to root K ion by C. Another thing here, for weak electrolytes, okay, and this is only for weak electrolytes, and it's very important that alpha, you can see, okay, the alpha value or the degree of ionization is proportional to 1 by root C. Okay, this is not alpha, this is proportionality sign over here. So it is proportional to 1 by root C. That is the ionization, okay, or the degree to which the electrolyte is ionized or dissociated is inversely proportional to its concentration, and this is true for all the weak electrolytes. Okay, that as the concentration of your electrolyte increases, okay, the alpha value will decrease. Okay, even though you will have more of products, because concentration is higher, you might have absolute amount of product, but the extent to which the electrolyte had dissociated will be low. Okay, the actual amount of product, that is actual amount of H positive and the actual amount of A negative with you, is equal to C alpha and C alpha. So it depends on C as well as alpha. Okay, so obviously if C is higher, the actual amount, the actual concentration of your products will be higher, but the alpha value will be lower. Okay, that is the extent or the degree to which your electrolyte had ionized will be lower, whereas if the concentration is low, the alpha value will be high. We'll come back to this concept later on when we study degree of ionization in further detail. Okay, for now this is all that you need to know about weak electrolytes. So whenever you have a weak acid or a weak base in the examination, for example if you have ammonium hydroxide, okay, then just assume that alpha there tends to 0. Okay, and then you can write that NH4 positive and OH negative. Okay, these products are C alpha and C alpha, and this is C into 1 minus alpha, where alpha can be assumed to be 0. Then solve for alpha, substitute that alpha value over here, and you will get the exact concentration of ammonium ion and the exact concentration of OH minus. Now here you cannot directly say that alpha is 0. Okay, and hence the concentration of ammonium ion is C into 0, that is 0. Okay, we can only neglect alpha when it is with respect to something. Okay, like we just saw for 1 rupee case, that the neglecting part of 1 rupee depends on how much you actually have. So here alpha can only be neglected or taken to be 0 when it is present with something even larger. But here alpha is not present with something, it is not being added or subtracted from something. Okay, it is present in absolute terms, and hence its exact value needs to be taken into account while calculating the concentrations of your product. Okay, so weak electrolytes is going to be the focus of our analysis in this entire chapter. Okay, so this is very important. Sometimes you also get questions on strong electrolytes and moderate electrolytes, but pretty much more than 95% of your questions are going to be based on weak electrolyte, and hence you should understand this concept in a very clear way. Okay, so make sure you don't have any doubts here. Watch the video again in case you have any doubts, and if still you are facing some problem, leave the comments and I will get back to you. Okay, so until next time, and once again thank you for watching Edupedia World videos.